Hello. Forgot to take up the cover of the camera. Welcome to CS302 Online. Today we're going to be talking about heaps. So, heaps. Before we jump into heaps, even though I said that we're talking about heaps, let's talk about how to store a binary tree in an array. So far, we've been working on storing them in essentially pointers, kind of like linked list style, right? But now, and I mentioned it already at some point, but better refresh you on that. But now we're going to talk about a way of storing the same tree in an array format. So I guess if you hate pointers, then this is of course one way to solve that issue, because there's no pointers involved when you're dealing with just a tree. So the way you do that is, of course, we got to go back to the different types of trees that we had, like complete, full, and balanced. Well, not balanced, complete, full, and what was the other one? Perfect. Yeah, perfect tree. And in this case, it's going to be the one that was a full tree, right? So actually, was it full tree or was it complete tree? Let me check. Full tree. No, full tree is the one that has 0 or 2 children. So it's a complete tree. Yeah, complete tree. Okay. So that's if you guys don't remember, this is has different names for the different properties. And so what I mean with a complete tree is that it's a tree that has every single level full with the exception of the last level. And that last level, if it's not full, then the nodes that it does have are all shifted as far as they can be to the right. So if we have a tree that looks like this is considered to be a complete tree because every level is full actually. So that works out too. But if we have one level that's not full, then it has to be the last level, and then all the nodes have to be as leftmost as possible. So that's considered a complete tree. So is that. So is that, so is that, but then this is not, because they're not allowed to put a node there. You have to put it here. Now, if you have a tree that is complete, then it's very easy to store into an array, because all you do is basically do the level order traversal going from left to right on each of the levels, and essentially just print out that order, and that is the order that is stored in the array. So suppose that we have the following tree. I was gonna write Halloween, but that's a lot of letters. So I'll just put Hallow. Okay, so in that case, the way that you put it in the array is you literally do the level order, which is Hallow. I guess whatever, we'll do Halloween. I don't know. Is that how you spell Halloween? I think it is. It looks weird like that. I feel like we're missing a letter somewhere, but okay. That would be the way you store it. Now, you can't put the end of Halloween here. That does not work. It doesn't work anywhere but here, actually. So there's only one way that this tree can be represented if it has Halloween in it, and it has to be this way. So how do you handle trees that are not in this format? Well, you can convert a tree that's not complete into a complete tree by filling all of the empty spots that should be full with a placeholder character. And that's kind of what you were doing with your assignments, right? So let's say we're making the tree James Bond. Okay, let's not get too carried away with this. So James, maybe we do actually there and ND. Okay, so the level order traversal of this is James Bond indeed. In fact, let me put it for you, and you can see that by seeing level, 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 level. Okay, however, it's not complete tree. It's not even a full tree, because as I refreshed a minute ago, a full tree is a tree that has 0 or 2 children. Here you can see nodes that have 1 child. And so the way we can convert it into a complete tree is by filling all the spots that should be full with a placeholder, which in this case, we're going to use this character, but you can use whatever you want. So for example, here, there's only one child, so we're going to throw in another child. Same here. And then that makes this level okay, but we still got the next level to worry about. So we can't just go ahead and say, oh, okay, let me just go ahead and add one here and one here and call it a day. Not quite, because technically speaking, our placeholder has to have children of its own like that. Actually, this B, let me shift it a little bit this way so it doesn't look out of place like that. There we go. Okay. And then similarly here, let me shift this a little bit so that we don't run out of space. This has to have two children of its own, like that. You see that? So this level has to have 2 to the whatever the level is. So in this case, it's 2 to the 4, or actually, well, 2 to the 3, because if we consider this 0, 1, 2, and 3, then this is 2 to the 3 to find out the number of nodes there, which should be 8. So we can see that we have 2, 4, 6, 8, of which only 2 are actual nodes. The other ones are placeholders. So we have 6 placeholders there. And so in this next level, we're going to have 2 to the 4th number of nodes, but we only have 2 real nodes. So that's basically going to mean that we are going to have quite a bit of placeholder nodes. In fact, we're going to have 2 to the 4 is 16, so 14 of those. So I'm just gonna put a different color for those, because otherwise it'll be too confusing. So those are gonna be that, and then there's 2 more here, which I gotta move that as well. So move this as tight as possible so that it fits. Okay, so then these are placeholders as well. 2 of them there, and then 2 here. And then each of those has 2, 2, and that's it. Actually, technically speaking, you don't need to have these afterwards. Yeah, you can pretty much quit at the D, because that is actually considered a complete tree, right? If, however, the D was like over here, like beneath the O, like if the D was there, then yes, you would have to put all those placeholders there. But in this case, we don't actually need that, because the last valid letter is there, and that is considered a complete tree. So now, if we were to do the level order traversal of this complete tree, then that would be JAM %E %S %B %O, and then 4 more percents, 1, 2, 3, 4, and D. Okay. So hopefully I don't make a mistake. So here we got %S, and then 2B, or not to be, I guess. That is the question. Okay, yep, everything is good. So this here is what you would store in your array. Now you might ask yourself, why does it have to be a complete 3? Well, it turns out that the reason we do that, and they probably noticed that in the assignment of one of the in the assignment that there was 6 or whatever, is that because if you do this formatting, then you can very easily, because remember, we're storing the tree just like this, like that's all we're storing. We're not storing any pointers, nothing. Like I'm telling you that as long as it's a full tree and you put your placeholders or whatever, then you can rebuild the tree from that single traversal, essentially, because it's a level order traversal, right? And you're like, well, before we had to use 2 traversals, etc., right? Because those were not necessarily complete trees. They could be just any tree. This is the requirement that it's complete, and that's why that works. So if you want to build this back, it's very easy. You just keep inserting as they go. However, what you can also do, and this is what you did in the assignment when you did your recursive insert function, is that you can locate the child of any node by taking that index, multiplying that index times 2, and adding 1 to it or adding 2 to it. Alternatively, you can just take the node, the index, multiply times 2, and then that version times 2 plus 1. Both of these will work. The difference being whether your index starts at, I think this is at 1, and this is, or sorry, index starts at 0 for this one, and this is for at 1. What that means if your array counting starts from 0 or 1, okay? So in this case, let's go ahead and number these indices. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? And if this level was complete, then this should go up all the way to 32 or 31, I suppose, right? Because that would be 2 to the 4 minus 1. So, or sorry, 2 to the 5 minus 1. Because remember, the property about how many nodes in the least amount of levels possible can be computed by saying 2 times the height minus 1. So that would be 2 to the 5th would be the number of nodes here, which is indeed 32 minus 1, which is 31, okay? But we don't have all of those because we don't need them. So anyways, the point is, if we look at the tree here, we can see that the right child, or let's look at a node that has 2 children. So like, let's look at, let's start actually with the root. So we have this, right? So the root is located at index 0. So if index 0 is the root and we want to find the left and right child, I'm claiming that you can find the left child by multiplying that index times 2 and then adding 1 to it. So 0 times 2 is equal to 0, plus 1 is equal to 1. That is indeed where the A is located, which matches that. So as for the right one, 0 times 2 is equal to 0, plus 2 is equal to 2. That is indeed where the M is located. Would this work where the indices counting from 1? Well, if they're counting from 1, then it would be at locations 2 and 3, right? So in that case, if we took 1 and multiplied it times 2, then we get 2 out of that, which is indeed where the A is. And if we took 1 and multiplied it times 2 plus 1, then that will give us 3, which is indeed where the M is. So as you can see, both of these work. Both of them you can implement. It just depends on how you keep your indices. If you're doing it all like we pretty much do because we're used to coding, and you do from 0, use the left-hand side formulas. But if you feel like doing it in MATLAB or something where like indexing starts from 1, then you just do the right one. As you can see, it's just a shift of 1. That's it. Big deal. So, but it's important, I suppose, because otherwise you screw everything up. But let's look further and see if this works. Like, for example, let us see what the children of S are. Okay, so we're looking at S. So that should be, it should tell us there's only one child, and then this should just be a placeholder, right? So where's S? S is index 6 right here. So that means that the children should be at 6 times 2 plus 1 for the left child, and 6 times 2 plus 2 for the right child. So this, of course, is equal to 13, and this, of course, is equal to 14. So if we look here, we can see that 13 is a placeholder, which makes sense because there's no left child. But 14 is the O, which is indeed what the left child, what the right child should be. So therefore, this works. So, okay. So why am I going over this again? I mean, because it kind of leads into heaps, and also if you're still stuck, I suppose, with this stuff, then hopefully this clarifies some of that just for your reference. But okay, so does anybody have any questions about how this array representation of a tree works? I'll take some water while you guys ponder that. Okay, that's fine. So then we shall move on to talking about heaps then. So heaps are indeed going to be implemented using an array version of a tree. But before we even talk about how they're implemented, let's talk about the concept of what a heap is, and specifically a binary heap, because there's also binomial heaps, which you'll learn in analysis of algorithms. I'm not going to go over those in this class. Plus, I probably couldn't off the top of my head. It's been a while. They're weird. So binary heaps, though, are very easy compared to the binomial heaps. Those you will pick up pretty much in one class. We'll be done with heaps after today. So, yeah, okay. So there's two kinds of heaps, really. There's a max heap and a min heap. And there's a very tiny difference between them. So I'll just pick one. Unless you guys have a preference, now's your chance. You want to see max heaps or min heaps? All right. So I don't know if there's a big delay. So I'll just pick one, I guess, unless somebody says something. So I'll just pick. I wonder which one I did last semester as an example. That's hard to remember. Which one's harder? They're like literally the same level of difficulty. It's like sorting in ascending order versus like sorting in descending order. So I'm gonna go ahead and close my eyes and pick something, I guess. Okay, that landed closer to the max. So we're gonna. It landed on the P of the max actually. So that's like next to it. So okay, we'll go with max heap, I guess. So they're really, you'll see. Okay. So anyways, all right. So what a heap is essentially an ordering of your tree. So first of all, flush out of your mind, at least for now, binary search trees. We're going back to just binary trees, and those are the hierarchical data structure, okay? We are still going to store numbers or characters in our trees, but what we are trying to do is organize it so that in the case of a max heap, the biggest number is at the top of the tree. So think about we're actually trying to organize like car ratings, safety ratings for cars, okay? I have no idea where that came to my mind, but that actually kind of works out. So the higher the number, I think is a better rating, right? Like maybe accurate, maybe a percentage of like survival in a crash, okay? Yeah, so we want 100%, right, to survive. But yeah, so what that means is that if we have 3 cars and they have a car rating of 90% survival rate, then one of them is 85% survival rate and the other one is like 20% survival rate. What we want to do is we want to organize them so that the 85 is the parent because, or sorry, not the 85, my bad. The 90 is the parent of both of these because 85 and 20 are both smaller than 90. So the biggest number, the max value, is always going to be on the top of it. So you can think of this like a ranking system or like a tournament where like this is the winner of the tournament, like the top of it. So let's say that another car came into the picture. Let's say that I don't know, we got, I don't want to like name car brands and then get in trouble for like talking crap about a car brand or something. So let's say we got a car that has a car rating of 70, okay? Where is that gonna go? Well, that is technically lower than both of these, but it's higher than this one, okay? But it turns out that with a heap, when you're building the tree, the first thing is it has to be a complete tree. So, I mean, surprise, we've been talking about that for the last few minutes. And also, it doesn't matter the ordering. So while I actually drew this like this with a 90, 85, and 20, I could have just as well done this. It doesn't matter the ordering of the level. It just matters that the parent is bigger than both of the childs. So in this case, for us to be able to put the 70, it will technically go here. And that's okay because that is still a complete tree and the heap property is maintained. So what is the heap property? That's an important term that we should know. The heap property is depending on whether it's a max heap or a min heap. And I guess I'll just put a line that the parent node has to be, and then line, than both of its children, or one if it only has one, you know. It's okay to have one child there. Now, why did I leave a line there? Because if it's a max heap, so max heap, put the word greater than, or just greater, and min heap, you can put smaller. But I suppose greater than or equal. So yeah, because equal is okay. So let me scroll that over so that I can put that. Greater than or equal. Although Yeah, because it doesn't really matter whether it's kind of like ABLs in that way that equality is not that big of an issue here. But if you find two nodes that are equal, yeah, it doesn't matter. It really doesn't matter if you put it beneath or above, as long as it's like next to each other. So we'll leave it like this, okay? So basically what I'm saying is the parent node, if it's a max heap, the parent node has to be greater than both of its children or equal to. And then the min heap, it has to be smaller than. So as a quick example, the min heap, let's say this is like placings on arrays. First place has to be, above second and third place, which could be redrawn as this as well. It doesn't matter. We don't care about the ordering of the children. We just care about this heap property. Any questions on the heap property? It's just something very trivial but very important for us to be able to follow the rest of this. Maybe we'll pick more examples. So if we have a value of x as in a max heap, and then we have a question mark here and a question mark here, which we'll call like y and z. What range of values can be y and z? Well, y is equal, or actually y is less than or equal to x, and the same thing for z. Z is less than or equal to x, and in relation of y and z, it doesn't matter. It could be greater than, it could be less than, it could be equal. Actually, they can be anything. There's no I don't even know what the math symbol for that would be actually, but it could be just about anything. Like, I'll put the word anything, I suppose. I kind of put myself in a spot here because I don't know what the symbol would be for that. Math people out there, what will be the symbol to say that y can be anything that z can be? Is there a math thing for that? So what if you had two 90s in the example above? So if I had two 90s like this, I could just as well do this. I could also do something like this. Oh, I the same thing, fail. There and there. Or in the example up here, if I had a 90 though, okay, so this comes into a situation. We haven't talked about how to move things around, but if I needed to put another 90 in this thing, I really have two options. I have to move one of the childs. I can either displace the 85 or displace the 20. If I displace I haven't talked about how I'm going to do this, but I have to do something like this. I have to put the 90 there and then put this as a child, essentially, somewhere here. Like, well, actually, it can't be there because this is a complete tree. So I just have to put this somewhere else. So maybe like there. That would work. Alternatively, I could go back to how I had it. And then maybe like put the 90 there. And then put the 85 like that. That works too. There's a lot of things that I could do. Of course, there's an algorithm to do this easily. But, we haven't talked about it yet. So anyways, essentially, and let me make sure I put here, this is a max heap. And for min heap, this would be y is greater than or equal to x. And then z is greater than or equal to x. And then y and z could just be whatever they want between them. Like, one could be bigger. Like, I could have, a 90 here in a max heap. And then I could have like a 1 here and an 89. Or vice versa. Like, there's really no relation between these. Like, they could be whatever they want. That's where I'm saying kind of like, take away from your brain the binary search trees and how like left is smaller and greater than. In a heap, we don't care whether something ends up on the left or the right of the parent. We just care that it's a child. It's kind of like directories in your computer. When we were drawing, I can scroll up here for like 5 minutes to find it, but I think we remember. When we were drawing the first day about trees, and I gave you the example of the file system with my directories where I had like 302 folder and 202 folder, and there was a syllabus folder, etc. I didn't care in what order I put the subdirectories. I might have put them alphabetically because we tend to go that way, but that's the problem. We want to separate ourselves from that. We don't care what order they are because they're just there. Like we know that inside of this directory, there's a bunch of files and we could order by anything we want or just not order, which in this case is we're not ordering by anything, right? So like if you right click on your directories, you can say order by date created or ascending, descending, file type. There's more than one order, right? Think of this like any order. We just kind of YOLO it. Okay, so that's the heap property and that's the basic concept of a heap. So the rest of the lecture is basically of how to basically put things in a heap, how to maintain this heap property, how to delete things from the heap, and so on. And usage cases of a heap, which we will get to. Okay? The best, by the way, off the top of my head, the best example of a heap is to create something known as a priority queue, or like a BIP queue, essentially. So we know what a queue is, right? You know, first in, first out, how you line up on like a grocery store to pay for something, or pretty much anything in life that you're trying to do organized, right? That's a normal queue. Priority queue is the same idea. However, there's like a VIP pass. So like people that have a VIP pass cannot automatically be kind of moved up the queue. So yeah. So with identical elements, they can be on either side, but inserted about smaller elements. So the only thing you have to be careful about with identical elements is that it does not violate the heap property. So if you've got something like this, doesn't matter if here's a 1. And by the way, you could have like a 2 and a 3 here, and then you could have like 89 and 88. You see, heap property is maintained because we got a 90 there, and 90 is same, so it's okay to be there. I mean, the 1 is smaller, so it's okay. 89 and 88 are smaller than 90, so that's okay. 1, 2, 3 is also okay technically. Actually, no, my bad. 1, 2, 3 is not okay because I switched to the min heap. Okay, now it's okay. Yeah. Yes. I didn't think about that, but yes. But see, you guys got it because you corrected me on that, so that's good. So yeah, so this would be okay. So you can see there's like absolutely no relations between the left and the right child. You know, this could turn out to be like, this side is like super heavy. So like, you know, bunch of numbers that are really big, like 70, and then here we have like, obviously they have to be smaller then, right? So actually, here's a good example. So like, here, let's say there's an 80, and then like, there's no 80 here until like here, and that's still okay. And then there could be like a 1 there randomly, and then there could be like a 90, or not 90 here, maybe like a 60, and then I gotta fill the rest of this tree. So maybe here there's like a 5, a 9, and then like 1000 randomly there, and then like a 2 there. So you see, this is still heap property, unless I screwed up something. Like, it's still like 90 is bigger than both of these, or equal to, so that's fine. Here, this is like 90 is bigger than 89 and 80, so that's okay. 3 is bigger than 2 and 1, so that's okay as well. 89 is bigger than 87 and 70, so that's okay. 87 is bigger than 80, so that's also okay. 80 is bigger than 1 and 60, so that's okay. 2 is bigger than 5 and 9, so that's okay. 1 is bigger than 1,000 and 2,000, so that's not okay, actually. So maybe we put that there, and then put the 1 there. Okay, so I screwed that up then. So this, I keep mentally switching to the min heap for some reason. Sorry about that. There we go. Okay, fixed again. Yep, fixed. I guess I'm used to thinking min heaps. So yes, but now it's max heap. So that 80 is bigger than 1 and 60. 9 is bigger than 5 and 2. And then, okay, let's kill the 1000. Because that is going to ruin things, okay? Bam, 1000 is killed, okay? Because the 1000 should actually go to the top because it's the biggest number. So yes. Let's say it was negative 1000. How about that? Negative 1000. Solved. Okay. So anyways, what I'm trying to make as a point here is that you have to disassociate the idea of left and right mattering. It doesn't matter in this case. We're equal opportunity for the sides. Okay. Oh, did I screw somewhere up? 4 is bigger than 3. Ah, yep. Okay, good point. -1. All right, now I think it is fixed now. Okay, so as you can see, trying to randomly do this is very prone to errors. Case in point. So now what I'm going to show you is how to do this without running into these errors. Case in point. So there's two algorithms that we want to talk about with heaps, and one of them is I love the name of this. It's called Heapify. It's like Heapify. Like Heapify me, Heapify this. It should be like one of those like ShamWow commercial kind of things. Okay, so there's a Heapify algorithm. That's my favorite name for an algorithm. And then I suppose there is like the this one doesn't have a real name, but kind of like bubble up, down. I suppose technically speaking, yeah, they're both because for insertion deletion. So basically insert and delete. Trying to think. It's always bubble up, really. Well, no, technically it's both, but yes. Just don't think of bubble up as insert and like bubble down as delete. They're both bubbling, okay, in both directions potentially. So, let me start with. Do you guys have a preference? Heapify or bubble sort? Let me tell you what each one does, and then maybe that'll guide which one you want to know first. Okay, so when this again is something that totally separates itself from ABL trees and other stuff. With ABL trees, you balance as you go, right? The whole purpose of like balancing as you go is that you can actually achieve that log-n height every time you insert. So you end up with potentially n log n if you were doing the in-order traversal to print out the sorted list, right? Heapify is a little bit different than that. Heapify, what it does is it takes a existing tree that's already a complete tree. So, you know, it has to, notice that I've been doing that. Like, I've actually been trying to keep track of that, making sure that they're complete. See, it's complete tree. I didn't put anything randomly there, right? So it takes a tree, any tree that is in complete format, and what it does is it heapifies it. So essentially, it converts it into a valid heap, max or min, depending on your choice. So by that, I mean that I could literally take an ABL tree that's so beautifully balanced and made and everything, as long as it's a complete format of it, and then turn it into a heap, which means it's just going to like blob everything up to make it into like the biggest numbers on the top. So that's what Heapify does. It does it at one go. And then the bubble up and bubble down is when you want to insert something into the heap or when you want to delete something into the heap, you always do that at the end of the heap. So like if I wanted to insert something into the heap, I would do it right there. That's the next available spot. So I would put it there and then I would let it fix itself, the heap to fix itself. Not calling the Heapify algorithm, because this is what people do. Like I didn't happen last semester too much, but in the past, like I would tell them like code a heap for me. And then when they insert something, they would insert it and then like call the Heapify algorithm, the entire Heapify algorithm. I'm like, no, that's horrible. That's inefficient as heck. What you want to do is you just want to fix that part of it. It's a little bit like ABLs where, you know, if one side is unbalanced, you know, and then you fix that, you don't need to recompute the height of the side that you didn't touch. That's still untouched. So no need to look at the heights of that again. Only the height that you're actually working with. So kind of like that with Heapify. When you insert something there, all you potentially are going to have to fix in this is going to be, you know, this part of the tree. But maybe you won't have to go as far up as that. Because remember, it's kind of like when you're fixing, you know, when you're balancing a tree, you might only need to balance like this part, right? And you need to modify. So it might just be that you just need to fix this part of the tree and everything else is still fixed. So like, for example, if I went ahead and I inserted a 88 into this, so I inserted 88 here, then the 88 is bigger than 87, so that violates the heap property, right? So I gotta basically figure out a way to fix that. But once I fix that subsection, which probably would result in me swapping the 87 with the 88, this is now fixed. So I don't need to go any further, right? Because this is still okay. 89 is still bigger than 88. So that would be like the equivalent of making a single rotation in AVL, and like everything is fixed now. Like the whole tree is okay. So yeah. So anyways, that is the other side of it. So inserting. So I think maybe we'll do the Heapify one first. So let's go ahead and do that. So let's come up with a set of random numbers and then do Heapify on them. So again, this is all kept in an array, by the way, but it's so much easier to show like this. So I don't know, letters or numbers. Let's do letters. Let's do numbers. I like numbers more with heaps. So I'm going to do pseudo random, but I'm going to do certain things here because I want to see special cases that, you know, might be useful for you guys to see. So let's do that. 12, 3, 2, 5, 11. Actually, no. 11 is easy to mess up writing, so 15. 2, 7, 1, 12, 1, 8, 7, and maybe like 21, 42. Okay, I think that's what I'll do. Maybe I'll make this a 77 randomly. Yeah, I'll do that. Okay, so let me make this a little bit wider on the first level so we have more space to work with. But other than that, I think we're good. Okay, so we have the following tree. It's just a random tree. In fact, I'm going to back it up by making a copy of it. And then we're going to use that later on to make maybe a min heap, okay? But for now, we're going to make a max heap out of this. And we're going to do that using the Heapify algorithm, okay? So our goal is to convert this tree into a tree that follows a heap property. The heap property being of a max heap that the parent is bigger than the child's. Okay, this is, we want to rate this by grade. Let's say these are all, oh, that's terrible, but okay. Let's say these are all grades from a test. That's pretty low. So we want to find out who got the highest grade and who got the second highest, and I mean, you know, we want to rank them up and see like who's the best person in the class, I guess, in the test or whatever. Okay, so terrible grades for, I mean, like, damn. Clearly there was 77 points if somebody got that, but then some people got like 1 point. So okay, so all right. Let's say this was an extra credit test. Okay, that way it doesn't look as bad. All right, so what we do with the Heapify, yeah, exam 1 scores, real data actually. No, it'd be great if we had the real data. If it wasn't because the TA, I put an ultimatum. He has to complete it before the drop date, so you guys know where you stand. So sorry about that, but okay. Anyways, so this essentially, you know, if you know, and I've never actually played the games, but I still know it. So maybe you guys too. You guys know the Triforce symbol in the Zelda games, Legend of Zelda games. You know, it's like a triangle, and then there's like triangles inside of it. You know, this is also like a fractal thing. If you keep going, making a bunch of triangles inside, it's actually like fractal stuff. You know, that's kind of what we're gonna do here, except upside down. You know, if we rotate the Triforce symbol like this, that's what we're trying to do. So we're gonna try to start by making tiny triangles, which will eventually converge into the big triangle, which is the entire tree. Okay, so the goal here is with the Heapify algorithm is you start at the end of the tree. So the last part of the tree, so in the array will be the end of the array. And remember, by the way, I didn't actually point this out, but maybe it was obvious, maybe not. So I should point it out. Suppose that in this example back here, we're looking at B, and we want to find out who the parent of B is. you can sort of reverse this algorithm to find out who's your parent is, right? Because how would you find it? What would you have to do? Well, look at the math. The parent is equal to, the parent's index. Well, here, the child's index is equal to the parent's index times 2 plus 1, or parent's index times 2 plus 2, right? So just do algebra and put put it on the other side. So essentially, if you do algebra, then you end up with 2p is equal to c minus 1, 2p is equal to c minus 2, and then divide both sides by 2. So you end up with the parent index being equal to c minus 1 divided by 2, or c minus 2 divided by 2, depending on if you're a left or right child. So, just go ahead and try that. So for example, for B, that's 9. So 9 minus 1 divided by 2 is equal to 4, right? And then 9 minus 2 divided by 2 is equal to 3.5, right? Essentially, because that's 7 divided by 2, so that's 3.5. So notice that the parent of B is indeed located at 4. So in both scenarios, if you take the floor function of this, so you round down, so you can do like integer division, you would end up with, my bad. You take the ceiling function, round up, then you will end up with the right index. So, because you got 4 and 3.5. So if you round up, not down, my bad, then you will end up with the parent. So if in your array implementation of a tree, you want to find out who's your parent, I guess, then just basically subtract 1 from it, or subtract 2 from it, and then divide it by 2. Frankly, just subtract 1 from it, because you'll get it right either way. But yeah, either one of these will give it to you. But if you take the second version, then you have to round up. But if you take the first one, you're good to go. Okay, so yeah, that's pretty much all I want to say about that. So anyways, when I'm talking here, I'm saying like, oh, okay, check up in the tree. What you're doing in code is you're just dividing that number by subtracting 1 from it and then dividing it by 2. Okay, so like if I want to find out the parent of this, take that index, which subtract 1 from it, and then divide it by 2. And then voila, you got the 15, okay? So it's important that you can maneuver that back and forth in code. Otherwise, taking this concept to code will be harder for you. Okay, so back to this. The way this algorithm works is we are going to take all of the leaf nodes and that sort of subtree. So that means take this subtree right here, and we're going to heapify that. And once that's heapified, then, only then, can we actually achieve to heapify the higher tree, which is this one. We can't heapify that one until we heapify the bottom one. Here's the reason why. If we try heapifying the green one first, then what's going to happen? Well, if we're looking at 12, 15, and 2, and we're doing a max heap, we can see that 15 has to be the parent. It doesn't matter where the 12 and the 2 end up, but 15 has to be the parent. Right? So regardless of which one you choose, you're going to have the same issue, which is the 15 is going to be replaced by the 12. So now, if you try to then do the heapify on the red one, then you're going to end up with 42 as the parent. So 42, and then I guess now you have a 12 there, so you have a 12 and a 21, right? But the problem is that you now have broken the green one, right? Because now the green one has has a 15 on the top, and then it has a 42 here, and then a 2 here, right? So you essentially broke the green one. So to avoid having to redo these things, work your way up. And as long as you work your way up into the bigger triangles, then you don't have to, fix things. So that basically you save time. So anyways, we're going to first do all of the smaller triangles before the bigger triangles. So that means we're going to do the red triangles first, which are these, and these. That's going to be the first sort of stage. In the second stage, we're going to do the green one. So we're going to do that green one there. And that's pretty much going to conclude the second stage. The third stage, Actually, technically speaking, the second stage would include also this one. The third stage is we're going to do the pink ones, which is actually just one of them. And then the fourth stage is going to be doing this one. And then we should be done. However, you will see that what this really looks like is going to be more like the trifecta, because when you're doing something like the second stage, the green one, even though I've only drawn the green on those three things here, you're really kind of considering this entire section here. Similarly here, you're considering this entire section. So now you can see how the triforce is going to form up. And this will be looking like a proper triforce if I drew it nicely, but it's kind of like thick triforce. So yeah. Nodes need to either have 2 or no children for it to work. No. So that will be a full tree, but no, this is a complete tree. So the rule for that is all levels have to be complete except for the last level. The last level can be incomplete, but all the nodes have to be shifted to the left side. Sorry, my left is your right. It's kind of complicated, but yeah, to the left side. Okay, so yeah. Okay, so anyways, let us go ahead and do that. So we haven't even started yet, and it's already kind of very messy, but it's colorful at least. So we're gonna do all the red triangles first, okay? So let's go ahead and just pick the first one. So let me just grab that and, you know, look at it. So we got 15, 21, and 42, okay? So what we want to do with that is we want to convert it into a max heap, which means look at all three numbers, pick the biggest one, and make that the parent. So in code, what you do is you compute, you compute those indices by looking at the two nodes that you have, which are 21 and 42, which are the last two nodes. Compute the parent by doing the thing where you subtract one from them and then divide it by 2. So that's how you compute the index of the parent. So now you have the location of the 15, the 21, and the 42, okay? Once you have the location of that, find the minimum of that or the maximum of that, depending if it's a min or max heap. In this case, it's a max heap, so find the maximum. So you find 42 to be the maximum, right? So 42 is the biggest number of them. What do? If it's the parent, you're done. If it's not the parent, then swap that with the parent, which means in this case, it's not the parent, so we're going to swap it with the parent, which means we're going to take 15 and 42 and swap them. And this is what defines where things end up at. So even though, like I said, it's okay, like we could have ended up with the 15 and 21 in different spots as long as they're children, the way it actually ends up in the algorithm, which again, it doesn't matter, it's just the way the algorithm makes it be, is you just do the swap with the parent. So wherever that happens to be is wherever it ends, okay? So anyways, now that we did that, we can go ahead and put it back in our tree. So leave it like that. Okay, we're not going to do the green square yet. First, we got to finish doing all the red squares next. So let's proceed to the next red square. The next red square is, let's take both of them at once. Okay, so we got these two squares here. Technically speaking, we got to look at this one first because we're going from the end to the beginning. So we got the 5, 8, and 77. It's a max heap, so the biggest number is 77. So we swapped that with the root because it's not the root currently. So that means that it's going to be taken up here. It doesn't like selecting small things. So I gotta like, come on. Okay. Let's just erase it and put it back in. Okay. So that takes care of that one. Let's go ahead and do the left one before we bring it back. So in that case, the biggest number is a 12. So that means that that is going to be the new root. It gets swapped with the 2, so the 2 ends up on the left side. Okay. Let me know if, A, if I make a mistake, and B, if you have questions, I suppose. Okay, so that's pretty much both our trees right there. So now we can put them back in here. Technically, they never left, right? I'm just kind of taking them out so that you can see. Let's see if that matches. Close enough for the trifecta. Triforce, not trifecta. Why am I thinking trifecta? Where does that come from? I don't know, but Triforce. Okay, So we got one more red square to do. We'll just do it in place here. So that one. So let us go ahead and start by swapping the 3 and the 7 because the 7 is bigger. Ends up there and the 3 is there. Okay, so all the red squares are finished now. We can move on to the green squares now, which is the second level. So when we see the green square, we see the 12, 42, and 2, right? 12 is smaller than 42, so we are going to swap that with the 42. Now here's the catch. When you do this, you have to check any trees beneath it that got affected, any triangles. So in this case, you need to re-verify this right here, the red square there. You need to verify that one more time. So it sort of flows down like that. And as you can see, it does indeed mess it up because 12 is and 21, you know, they gotta get swapped because 12 is smaller than 21. But here's the good thing about this. Unlike the other version where you just be going back and forth for a couple of times, potentially, in this version, if you follow this rule set that I'm going with the triangles, small triangles first, that's it. You're only going to have to fix that one time. You don't ever have to go back to it again. So as you can see, it does not break the green square. If we did it the other way around, it's possible that when if you first do the green one, it breaks the red, you do the red, it breaks the green again, you go to red, green again, so you got to go multiple times in circles. If you do it this way, then you only got to fix it one time. And so now, technically speaking, we've expanded the heap area to include those. Of course, there's nothing here, but if there was, that would also be, at this point, done. Okay? Cool. Let's do the other green square over here. So here we got a 77. That's kind of sneaky there, but it's pretty big, so that's got to go on the top. So that's the one we picked to swap with. Again, because we changed that, we got to look at that intersection. So we got to look at that red square. It turned out that in this case, it does not need a swap because they're equal. So we leave it be. However, you know, it's possible that it could have ended up with a swap. But that's why I picked these numbers, so we don't have to swap every single time. Okay? We don't need to check this one here. We don't need to check that one because the fact that this was already okay beforehand when we looked at them and we picked this as to be the biggest number, the 77, it means that we only need to mess with this because it guarantees that this 77 is going to be bigger than whatever is here, okay? If you don't kind of fully grasp that, just think about it with some examples, okay? We had 3 numbers here. We picked of these 3 numbers the biggest one, and it turned out that the biggest one was over here. Because of that, we are putting that here as the biggest number. It's impossible for this one to be bigger because otherwise we would have picked this one, right? So that's why you don't need to worry about fixing anything here, only on the side that you pick something from. Okay? And also because this number was bigger than this, it's possible that this might have been broken because of that swap. So that part also makes sense. So really, this is all about really kind of getting a feel for it. Okay, so now we finished out of the phase 2. Now we go to the pink one, which is the phase 3. In the phase 3, we got the pink triangle, so we can see, or purple, whatever this is, we can see that the 42 is the biggest of the numbers. So that's going to get swapped to the root place. So 2 and 42. So now here's the catch. This side is okay, but this side we got to fix again potentially. So, and this can bubble all the way down too. So as you can see here, this is indeed what is going to happen because 21 is bigger than that. So 21 goes there and the 2 goes down. So now because of that swap, we still need to check this red one again. Now you might be thinking, but you said we would never check it again. Right. You will never check it again in relation to the green and red, but not to anything above it. So we might actually even go back again one more time once we hit the blue. So it's only per phase you will never see it again, not that you never see it ever again. In this case, the 2 goes with the 15. So that goes there. Okay? So anyways, that takes care of the purple one. We go to the final phase, the 1, 42, and 77. We take the 77 and we swap it with the 1 because it's the biggest number. Now we change the green one on this side, so we gotta potentially fix this whole subtree. But not everything, just the side that gets changed. Because in this case, the 12 is the biggest one here. So the 12 is going to be put here, which means now this is okay. We just have to worry about checking this one. And indeed, we gotta swap this 1 and 2. The Triforce is complete. We have created a min heap. As you can see here, every parent is bigger than its children. 77 is bigger than 42 and 12. 42 is bigger than 21 and 7. 12 is bigger than 2 and 8. 21 is bigger than 15 and 2. 7 is bigger than 3 and 1. 2 is bigger than 1 and 1. 8 is bigger than 5 and equal to 8, so that's okay. 15 is bigger than 12 and 2. Not only did I say this to clarify, but also because I wanted to make sure that I got it right. So, got it right. Okay? So, there you go. That is a Heapify algorithm. It's quite trivial to do on paper, but it can get a little tricky when you're doing it in code. Just remember the whole indexing thing, and you should be okay. Just identify the tree indices of your root and your two nodes. Call them root and left and right child, and then pick the biggest one and then put that as the root, and then you'll be done with that subtree. And then find the next subtree by subtracting 2 from that, right? So like, or 1 technically if you're here. So like, if you look at how this is implemented, let's do an example where we're doing it straight from the array. Let's do a min heap now, but let's do a min heap with a smaller set of numbers, because otherwise we'll be here all day. So let's just go ahead and do something like 5, 4, 1, 2, 3. Okay. What would that look like? Well, that would look like something like this. 5, 4, 1, 2, 3. Yeah, that's good enough. Okay. Maybe one more number or 2 more numbers. 8, 7, and then I want to put here a 1. Okay? Yeah. So in that case, this would be 5, 4, 1, 2, 3, 8, 7, 1. Okay? So now we're going to go ahead and do a min heap. So that means we want the smallest one to be on the top. And then, of course, the smallest number is the one that's picked as the root. So just to make sure that everything is nicely separated so we don't accidentally do something we don't choose to do. Close enough for the lines. We have indices 0, 1, 2, 3, 4, 5, 6, 7. Though we start this as we take the last 2 indices. Actually, here's a little trick that you can do to make this easier. Notice something about where the left nodes are and where the right nodes are. So like the left childs in this tree are 4, 2, 1, and 8, right? Those are all the left children. 3, 1, and 7, the other 3, 1, and 7. So like this one, this one, this one are technically right children. So that one's the left and these are right, okay? Notice on where those are located here. The 7 is here. The 8 is here. The 1 is here. And then the 4 is here. The 2 is here. Oh shoot, I circled the 8 when I shouldn't have. So, okay, so we got the 4, we have the 2, we have this 1, and we have this 8. And then we have this 1, and then this 3. Okay, yeah. So notice something here. Okay. The red ones, yes. Oh, you set it up there already. There you go. So yes, the right indices are even numbers, and the odd indices are the left numbers. And the exception is, of course, the root, which is a special one because it's at 0. So yes, I should have looked up. So there you go. I was actually thinking for a second why it wasn't working, but then I figured out that the ones were flipped. So yeah. Okay. So if you do that little trick, then you can know whether you're working with a left child or a right child, and then you can also make the math easier like that. So if we want to look at a pair, you know, you can start, and also you can find out where a level starts by using powers of 2s minus 1s and things like that. So you can see, like, for example, minus 1 or plus 1, actually. I think it's minus 1. So 2 to the third minus 1 is 7. Yeah, so you can see that 2 to the 3 minus 1 is 7. 2 to the second plus 1 is 5. So that would be here. Oh wait, 2 to the second minus 1, not plus 1, sorry. 2 to the second minus 1 is here. Wait, why didn't that one work? That's 3. Sorry, I'm looking at the numbers, not the indices. But 2 to the second minus 1 is indeed 3, which is where that starts actually. And then 2 to the first minus 1 is just 1, which is indeed where that starts. So yeah, so you can use the powers of 2s to figure out where a level starts as well. That could be useful to know too. But anyways, so if we want to start doing this heap, we can go ahead and see that 7 is the left child and there is no right child paired with this one. So we are going to go ahead and find out what the parent of that is by subtracting 1 from it and dividing it by 2. So in this case, that would be 7 minus 1 is 6, divided by 2 is 3. So that takes us to this 2 right here, which is indeed where that is, right? So now we've identified that the root index is 3 and the left index is 7 and there is no right index. Okay? So it would be 8 technically, but there's nothing there. So none. Okay? So now you can go ahead and actually pick the biggest number. Again, these are indices though. They're not actual numbers. If you want to see the numbers, then that would be 2 and 1 and then nothing. So 7 is the smallest one, so that means that you do have to swap these, right? So you want to swap these two, which means that you're going to end up swapping. Let me just rewrite this because I kind of like this picture. It's pretty. So let me just rewrite that down here. So you're going to swap the 1 here. Let me just, okay, and then the 2, like such. Okay. And that basically takes care of that tree. So now the next one is the 8 and the 7, which you can see are the next 2 right there. Okay? So if you want to compute the parent of that, just take 8 minus 1 divided by 2. Well, not 8, sorry, the index 5 minus 1 divided by 2. That's equal to 4 divided by 2, which is equal to 2. So that is basically going to be that. Sorry. I keep mixing the values. This is why sometimes it's better to do letters than numbers when doing the indices. So I should have probably picked letters for this. But yeah, okay. So again, if we want to just take this whole thing that we did before, I'm not going to do this too many times because it does take a lot of time. But the root is located at index 2. The left is located at index 5 and 6. And so the values of that are actually 1, 8, and 7. Pick the smallest one. That's already done, as you can see. So no swapping needs to be done. We can consider this to be complete. Okay, we're kind of going into the second stage now, doing the 4, 2, and 3. So as you can see, this is where it gets a little bit interesting because the 4, the 2, and the 3 are not next to each other. You can see that the here is where the 3 is, but the 2, why is it the 2 got lost in this? We like copied and pasted and lost the 2 at some point. Oh no, I see, we swapped it here, or we never swapped it here. That's what it is. So I was still looking at the at that picture. Okay, so now it's okay. However, is this the one? 0, 1, 2, 3. Okay, yes. So these are indeed the 2 2s that we're looking, the one that we're looking at. Okay, so 1 and 3. So looking at the 1 and the 3 here, we can see that the parent of this would be located at 3 minus 1, which is 2, divided by 2, which is 1. So that is indeed where this 4 is. So that actually matches. So go ahead and just update this. So let me just update it. So the root is located, I just realized I used the word R twice. Maybe I should replace that with root. Okay, so the root is located at index 1. Yep, and then the left and the right are 3 and 4. And then here we have the values of 4, 1, and 3. Okay, it's very abstract to not see with the tree, so I like confirm, but That's the thing. That's why you want to draw it when you're coding it so you don't get confused. So pick the smallest one and make it the root. So here it's obvious that these are going to swap. So essentially we're swapping left and root. So before I forget, let me do it here. So left and root. Over here, that means we're changing this one with a 1, and we're putting the 4 here. However, because we swapped that, we need to make sure this didn't break. And it actually did, so that's good that we're checking. So how do we check that? Well, when we just swapped it, we know that we just swapped it with the left, which is at index 3, right? So index 3 is what we just swapped. The way to check its children is just times 2 plus 1 plus 2, right? So 3 times 2 plus 1, 3 times 2 plus 2. So essentially that is going to be indexes 7 and 8. Oh, well, take the index, not the value. Not index 3. Oh, no, that's okay. But the reason why is there's no 8, so that's okay. So this was okay. Yeah. So take 3 times 2 plus 1. We see that this is a valid index, which is 7. So that's where the 2 is. And we see that this is not an invalid index, right? How will you check if it's not invalid? I recommend that you just keep a variable called size that contains not the size of the array. Well, that's actually good to have, I suppose. But more importantly, that contains the number of valid nodes in your array. Okay? So that would tell you that there's only 8 things there. So that means there's no 8th, which will be 9th value in the thing. Okay? So, yeah. So now that you got that, then you do the same thing. But in this case, you see that there's nothing here. So you're really only comparing the left side with the root. So you're comparing essentially the index of the 3 with the 7 index with nothing here because, well, technically the 8, but there's nothing there. So what you're looking at here is you are looking at a 4 and you are looking at a 2 and you're not looking at anything here. So then, of course, that is when you find out that you have to swap them. So you can see how this is so much more like, you know, not hard, but picky. Like you have to be very careful when you're doing this and not make mistakes, which is kind of what it would look like in coding. Like this is literally how you should be coding this, the way I'm doing it right now. Yeah, so make sure you actually swap that. Okay. And so, what did I do there? I wrote them the same way again, I think. So now that you did that, you do the final triangle. So, you know, I don't want to do it at this point, but, you know, you're looking at these two now. And notice how it's growing by 2s here. This can be its own loop, unrelated to you checking other things down here. This could be a recursive call or whatever. But this is always kind of going in groups of 2s, as you can see, which is very, very nice, very easy to implement. So now you're looking at the 1, 1, and 5. Of course, the 5 is bigger. So in this case, you could technically replace it with either one. Just pick the left one to make your life easy. You got to pick something in code, right? So just pick the left one. Although here it's going to make my life hard. So you know what? I'm going to pick the right one so that I don't have to bubble anymore. Because if I pick the right one, I'm done at this point. Whereas if I pick the left side, I would have had to like move things around actually. Because I would have ended up with a 2 that has to be bubbled up and then the 4 that has to be bubbled up. Okay? But the same thing applies. Okay, so that is how you do Heapify in sort of code essentially. Actually in place with an array. It's a lot easier and it's okay to do in a test with the drawing. But yes, it can be very tedious to make sure you get all these indices right. But it's not hard because you're not dealing with pointers. So while yes, you can still sec fault if you go out of bounds, it's a lot easier to debug than when your thing just crashes from like a null pointer that shouldn't be there, but it's there and you're like, why is it there? So, and this is like very hard to do memory leaks on this because you're not doing anything with memory leaks. So it's actually one of the easier assignments. It's just tedious, okay? So I try to make it interesting. I picked Edge of Tomorrow as the topic for the assignment. So there's these... it's the first of 2 assignments based on this lore of Edge of Tomorrow, Live, Die, Repeat. There's a lot of memes in there for that. Please don't be offended by them. Some of them I realize can be aggressive because the Sergeant Farrell, I think is the name of the guy. He says these things and they're funny, but I was like looking at them earlier before posting and I was like, okay, maybe I should like change some things. So yes, but okay. We still got to do the bubble up and down. So let's go ahead and do an example of that. And we can always do one more example next time. So let's take this one though. Let's take this tree that we did. Maybe next time we'll do the big one with the min heap. But anyways, going back to max heap land. We still need to learn how to insert and how to delete. So let's just do insert for now, because delete is pretty much the same thing as insert, but backwards. So if you want to insert, you always insert at the next spot available in the complete tree. So in this case, it would have to be right there, the left side of this 2, okay? And that makes sense because in the array, that just means put it at the last spot in the array, like append it. Literally, if you're implementing this with a vector, you just call pushback and put it in. So let's say that we're, I'm going to not pick too big of a number so that we don't have to do too big. So let's say we're inserting a 30 in there, okay? The 30 is going to obviously have to be bubbled up because it's a max heap. So when you insert the 30, what you do is you sort of work your way up in the tree. You don't need to change everything in the tree. You just have to work on the subsections. So let me pick a color I haven't picked. So you work on this subsection first, which may potentially affect this subsection, which in result may affect this section or something like that. So we'll see. So if you go ahead and you pick that, you can see that of course the 2 and the 30 have to swap. And now you work on the green square and you see that the 21 and the 30 have to swap. After you do that, you don't need to check this down again because you just came from there. So like, and this was already a heap as it was before, so you don't need to worry about that. So yeah, that's I guess the one advantage of it. So I guess you didn't have to go that far down. That's pretty much all there's to it. Let's insert a 78. So it's like biggest number possible, right? That means it's gonna have to end up at the root somehow. If we insert a 78, it's gonna get swapped with the 21. And then it's going to get swapped with the 30. Then we got 78, 42, and 7. It's going to get swapped with this. But here's the cool thing. See how it's not breaking anything? Because it's already a heap. That's the good advantage of that. And finally here, we swap this with this. So yes. I might have been misleading to you when I said there's very little that you need to modify. You only need to modify it in your path as you go. The one where you do have to play things around is with the deleting. The deleting, how it works is as follows. Since we got 2 minutes, I can do a delete example. Let's say that we would like, first of all, it's important actually. You don't just delete anything in a heap. It's kind of like a queue where you just insert and basically call it NQ and then DQ, which is like remove from the queue. With this, there's only one place that you can technically insert, which is at the complete part, and then it just automatically flows to the right spot. And similar with the delete, there's only one item that you can delete, or one key they call it, and that's the root. The only thing you're allowed to delete in the heap is the root. And why is that? Because it's the biggest number or smallest number depending on what you're working with. And so the way you delete that actually is you swap it with the last item in the heap. So in this case, you'd actually swap it with the 21. And what is it, by the way, what is the last item of the heap? Is the last item in your array, right? So you, oh my gosh. So you swap it with the 21. Here, let me just, this looks messy. Let's just erase this part of the tree permanently. This is like messy. So there we go. It has disappeared from existence, okay? Don't worry about it. Just accept the fact that it's gone. Okay? So anyways, now I guess it gets swapped with the 2. So after you do that swap, you can either do whatever you want to do to delete this, or simply decrease the size of that integer that you're keeping in the array, so you basically know that that's no longer part of this, right? Because like, if you have your array, and then you have something at the end, but you increase the size, then it's as if it didn't exist, right? You just ignore it. So that actually works out pretty nicely. And then you can override it next time. So you just kind of forget about it. So it just disappears from your memory. Even though it's still there, you just kind of forget about it. So anyways, after you do that, of course, the heap is broken because 2 is like not by any means the biggest number there. So then you bubble down. So you basically do the same thing we did when we were heapifying it from that spot. So you just start with the 2, and then you put the 77 there because the 77 is bigger than the 2. And then because you messed that up, you got to check the pink tree now. And yes, that 42 is bigger than the 2, so that's what you swap it with. As long as you do that swap, you don't need to worry about this at all. Just like you don't need to worry about anything there. You only need to worry about this part now. Oh no, we had a number here, but it's gone now. Shoot. Oh well, let's just say it was like 17. Okay? So, yeah, okay. Anyways, so actually, because I want to show you something, let's just say it's a 13. Okay? So anyways, the 15 is bigger than the 2, so that gets swapped there. And then finally, the 2 and the 12 get swapped. And there we go. Now we have a heap again. Okay? So that's how you bubble up and down. We'll do more examples of that next time. But I kind of wanted just to show you the whole thing so that if you want to do the assignment this weekend, you can. In addition to that, I'd like to announce, I already kind of did, but didn't show it yet, is there will be a limited time engagement extra credit assignment for Halloween. And that will be posted as a video along with the skeleton code and some writing on Canvas between now and Halloween. And it'll be for a limited amount of time for you to be able to do it as extra credit. It'll be worth about 300 points, I would say. So, yes. Yes, we can extend ABL trees. That's fine. I don't know what's due at this point. Like, what do you guys submit already? But, yes. Well, as I said, I told the ultimatum to the TAs that they have to grade it before the drop date. So, yes. Okay? But still prioritize the ABL over the extra credit. But the extra credit will be there, and it will be basically worth the same as one assignment. So if you didn't do one assignment, then you can make it up like this. It's also worth the same amount that you get as if you were basically watching the lectures here. So lots of extra credit. The second midterm is, I don't think next week, but the week after that. So pending verification that we kind of have enough to do. I think we will, because Heaps is the last thing that we talk about in trees. So that is kind of nice, because then the test can be just on trees, like trees for life kind of thing. And then that'll be the focus of the second midterm. And then maybe hashing, depending on how far we get with hashing next week. And then the final will be like graphs plus some stuff from the other test. So yeah, this is the last of the big tree algorithms we do. And I will release the assignment for this. But we will do more examples of heaps next week, especially for the insert and delete. I'll try to go back and do it as an array and whatnot. Yes, it is indeed comprehensive. However, it has a heavy focus on the latter part, because at that point in time, I will have not tested you yet on like graph stuff. So that will be the main focus, but there will still be some questions, probably an ABL tree question and probably a recurrence relation question, because those are the ones that are the big ones. Does it get easier from here? Hashing is easy, but then when you go back to graphs, it's more pointers. So, you know, there's no escaping the coding pointer stuff. But like I said, ABL is the hardest one. Like, that's where you peak in difficulty, in my opinion. In my biased opinion, I think ABL is the hardest algorithm that you code, and recurrence relations is the hardest concept that you learn. The other stuff is easy for the most part. Although some of the graphing stuff, like minimum spanning tree algorithms, I don't consider them hard. But last semester when I was teaching it, I screwed it up and I had to re-record a lecture. So I found that hard, I suppose. But that's just because like I keep making the same mistake twice. Like I made it 2 times that I taught the course. This time I'm gonna like super try not to make that mistake. So we'll see how it goes. Well, that's because what you're learning in this class is easy, but actually making a good hash function is not easy at all. But that's not the purpose of the class. So it's like, it's easy to drive a car, but it takes a lot of engineering to actually create a car, kind of thing. And we're mostly teaching you how to drive the car. So, like, this is the accelerator pedal kind of thing. Versus like, okay, for the accelerator pedal to actually accelerate the car, there has to be like magic going on to like actually feed fuel into the engine and do other things. So, yeah. But yeah, I mean, it is Wednesday, yeah. So have a good weekend. Stay safe during Halloween. Don't do anything crazy. If you're bored in Halloween, then you can do the extra credit assignment. Otherwise, you can do it. It'll be a few days after Halloween as well, so you don't like feel compelled to do it during Halloween. But, you know, it'll be a cool assignment. And keep posted on that. I'll make a Canvas announcement as well. And the 202 class will be working on it as well. So it'll be both 202 and 302. So that's something to be said. If they do better than you guys, then you should be ashamed of yourself, right? But hey, if on Discord or whatnot, feel free to peek into the 202 channel. Maybe they'll be talking about the assignment too, and you guys can work on it. So, yes. That's it. That's all. Unless you want me to show you like video of the assignment, which like I have a picture of it. I have a picture of the code. I did show that to the class, so I guess I can briefly show. So, does it still compile? Okay, it still compiles. It requires these parameters, and I run it, and it's the Singularity engine, and if I press any letter, it moves, and it moves. Each thing is spawned in a random direction, but they always keep moving in the same direction. If they go to the top of the screen, they come back on the bottom of the screen. And then if I press A, it creates a singularity. If anybody touches the singularity, there's a 50% chance that they're going to get triggered. If they get triggered, you'll see it change to a little square. Oh, yeah, we got 2 of them triggered. And now we have multiple triggered nodes that are still going in a random direction. If those come in contact with some that are not triggered, there's another 50% chance that they will trigger themselves as well. Like the trigger will trigger other ones. Now it's just a matter of letting it play. As you can see, yeah, it's like zombies. They start spreading until everybody has been triggered, essentially. We have 1 survivor right now, 2 survivors. See, he's running for it. Will he survive? Oh, no, he just got taken. And so there you go. And then you press Q to exit. And these are basically the dimensions of the program along with the odds. If I want to decrease the chance of odds. I already forgot what pop does, to be honest with you. Oh, population. So like if I want to put more X's or S. So like if I want to try like a low population game, of course, you know, it's less squares, but I can put a bunch of singularities like this. And eventually, once one gets triggered, it's a matter of time until they all get triggered. But if there's low population, we kind of, what would you call it? Oh yeah, lower the curve. So, but eventually, unless we find some way to stop it, everybody's gonna get triggered. So it's kind of scary simulation of that. I was going to do this as a final project for 302 last semester, but then the whole COVID thing happened, and I was like, it's very out of taste to do something like that during this time. Now I think it's okay. Plus it's extra credit, so yeah. Plus it's themed to Halloween, not to COVID. So yeah. But yes, there definitely is a good simulation of like infectious diseases and whatnot. So yes. Anyways, that's the assignment. So I'll do a video describing it more and whatnot. So look for that between now and Halloween. Probably tomorrow I'll post it. I'm gonna record it after I go eat today, and then do some editing on it and do some write-up for that, and then post it. So it'd be spooky. So yeah, okay. Well, that's it. Happy Halloween. Stay safe, everybody. I'll see you guys next week. Keep posted on the extra credit, and then let me know about the ABL tree one to make it do, and then we'll do that as well. Okay? So, see you guys later. Have a good night.